Welcome. This is the video for the exercises for section 1.1. Now before we jump into the exercises, since this is the first exercise video, let me explain to you how I think that you can best use these videos. So these are meant to help you practice the material that you learned in the lecture video. The analogy that I always like to use for learning math is that it's like learning to shoot free throws. So you would not try to learn how to shoot free throws by watching an hour of YouTube videos of somebody shooting free throws and then go outside and expect to be perfect, right? You just know it wouldn't work out that way. Math is really exactly the same as that. Now, if you were learning to shoot free throws, you'd probably start by watching some YouTube videos. You would learn about technique and form, but then you would have to go out there and you would have to miss the first 50 before you started to get good at it. So the lecture videos are like that first step. You're watching videos, you're learning about form and technique and things like that. This video is kind of like that second step of going outside and starting to try to shoot free throws. So you should not just watch this video all the way through. That's not going to do you any good. I've picked out 5 problems here. And what you should do is look at each problem. So before I start problem number 1 here, you should try to solve it yourself. So pause the video before I even start and try to solve the problem. This is the first one from the section, so it shouldn't be too hard. If you get stuck, if you don't know how to solve it, then unpause the video until I say 1 or 2 things, and then pause it again and try to finish from there. Now, I know it's going to be really, really tempting to ignore this advice and just watch the video. But that can really lull you into a false sense of thinking that you know the material. It's really easy to watch somebody else solve a problem and think to yourself, yeah, okay, that made sense, I get it. But that's so much different from actually sitting down on an exam or on your own homework and being able to do it yourself from scratch. So I really, really want you to pause this video and try this first problem before you just watch the solution. I was an undergraduate who took math classes at one point too, so I know how tempting it is to just watch the video. But really, I'm going to keep saying this, pause and try to solve this problem. Okay. So now I'm going to work through it. I very intentionally didn't solve these problems ahead of time because I don't want you to sit here and just watch me say the answer. I want you to see the process of solving the problem. So I've got the problem here, and like with all problems, we're going to try some things. Maybe it'll work the first time, or maybe something will go wrong and we'll have to go back and try again. Maybe we'll make a mistake and have to fix it. I just want you to see the process of problem solving. Okay. So this is exercise number 1 from section 1.1. It says the population of a city P, so I'll circle that just so we see that's an important variable, in millions is a function of T, the number of years since 2010. Okay, so we've got P is really a function of T. So time changes, and as a result, the population changes. Explain the meaning of the statement f of 5 equals 7 in terms of the population of the city. So this doesn't require any real calculation. This is just trying to see if we understand how we can turn data into functions and back and forth. So f of 5 equals 7. Well, that means that the 5 is in place of the t. And the 7, that's the output. So that's like our p. So remember the way that we think about a function as a black box. You've got your input t. Something happens, and you get your output p. So you're feeding it through. So what does it mean when t equals 5? Well, it says t is the number of years since 2010. So that's 5 years since 2010. That means 2015. And we get a p of 7. And the problem tells us that p is the population of a city in millions. So that gives us a population of 7 million. So let's write this in one nice answer. Explain the meaning of the statement f of 5 equals 7 in terms of the population of a city. What it means is that in 2015, the population of the city was 7 million. Okay, so that's our answer for number 1. Hopefully not too difficult. Moving on to number 2, and again, you should pause, try to solve this on your own, and if you get stuck, start watching again, or when you think you have the right answer, watch again and see if you get the same thing that I got. Now, let me just say right here, it's always possible that I could make a mistake and not realize it. If you think I made a mistake, check with a friend in the class for starters, and if you both think I made a mistake, then send me an email and let me know so I can fix it. Okay, so this is exercise 7 from the book, and the instructions encompassed a few exercises. It says, find an equation for the line that passes through the given points. So let me summarize. What this question is asking us to do is turn 2 points into the equation for the line. Now you notice that this is not an example that we directly did in the lecture. We kind of mentioned it with one of our graphs. This is kind of a typical exercise for this textbook, and it's one of the reasons that it's a pretty good calculus textbook, is that some of the questions in the exercises expect you to kind of use some critical thinking and figure some things out on your own. It's not the case that for every single exercise you can just go back and find the example that does the same thing, because then you're not really learning, you're just copying. So what we're going to do is think about what information we have. We're going to draw a graph, and we're going to see if we can figure out a way to deduce the equation for the line from this information. So when in doubt, I think it's always a good idea to start with a graph. So let me draw some axes here. We're going to plot our 2 points. We've got -1, 0, so that's 1 to the left and 0 up. That's -1, 0. And then we've got 2, 6, so 2 over 6 up. It's not exactly to scale, but it doesn't have to be. We're not going to use the picture to actually get our answer. We're just going to use it to kind of think about what's going on. OK, now let's draw the line between them. Let's see if I can make this a little bit better. There. Oh. This app is a little finicky about trying to lock into different things, but that's pretty close. OK, so the picture makes it look like it has a y-intercept of 2, but we don't know that's the case. We can't rely on us having drawn the picture to scale. So we need to try to figure this out on our own. Now let's think, what do we need to find in order to know the equation for a line? Well, the book told us the equation for a line is y equals b plus mx. X and y are your variables. Those will always stay variables. B is your y-intercept, and m is your slope. So if we can find the slope and the y-intercept, then we'll be good. We just plug them into this formula. Let's start with the slope. The slope is usually a better place to start. We said that the slope could be written as rise over run. Another way to think about that, or another way to phrase the same thing, is the change in y over the change in x. Now this is the first time you might see this symbol here. This is a Greek capital delta, and this means change in. So change in y over change in x. So let's look at our 2 points. As we go from the left point to the right point, how much does the height change? Well, we start out at 0, and we go to 6. Now, so that we don't have to do all the arithmetic in our head, we can write that as a subtraction. How far do you go? 6 minus 0. How about x? You start out at -1, and you end up in 2. So how far do you go? 2 minus -1. Now that's 6 over 2 minus -1. That's 2 plus 1. That's 3. For a slope of 2. OK, so we have our slope. The next thing we need is the y-intercept. And you have to be a little bit more clever here. There's not just a nice formula, at least we don't have a nice formula yet, to plug in. So let's think about what we do know. we know that we're going to have an equation for a line that looks like this. And now we know m. So far, what we know is our equation is going to have the form y equals b plus 2x. And the question is, what is b? Well, the information that we can use to figure that out is that we know two different points, negative 1, 0, and 2, 6, that are supposed to make this equation true. What that means, what does it mean to make an equation true? It means if I plug in negative 1 for x, I'm supposed to get 0 for y. If I plug in 2 for x, I'm supposed to get 6 for y. So let's do that in this equation. We only need to pick one of those points. Let's plug in the x value. We know what the y value should be, and that's going to leave one unknown, which is b, which we can solve for. So from this point here, we know that 0, that's the y value, equals our unknown b, plus 2, that's our slope, times the x value, that's negative 1. So this says that 0 equals b minus 2. Add 2 to both sides, and we get b equals 2. So that's our y-intercept. So here, we were lucky. Our picture did make sense, but depending on whether or not you draw it to scale, whether your line is straight, you can't always rely on your picture. Now, what you can rely on your picture for is just a little bit of a mental check afterwards. If you had this picture and then you figured out that your slope was negative 50 and your y-intercept was negative 100, you would look at this picture and say, well, that can't be right. That's off by too much. But it's not going to tell you whether it's exactly 2 or maybe 2.5 or something like that. Now, to finish the problem, we have to actually do what it says to do, which is find the equation for the line. But we have all the parts. We have the slope, that's our m. We have our y-intercept, that's our b. And so we're ready to write our final answer, which is y equals 2 plus 2x. And this is our final answer. Now, almost all the time in calculus, you can check your answer in some kind of way. Sometimes it's a little tricky to figure out how, but this is easy. We have an equation that we're claiming both of our points satisfy that equation. Well, you can just check that. So let's check. When we plug in negative 1, do we get 0? Well, that's 2 plus 2 times negative 1. That's 2 minus 2. That's 0. Okay, so that one's good. It also says that when we plug in 2, we should get 6. So let's see. When we plug in 2, we get 2 plus 2 times 2 is 4. 2 plus 4 is 6. So that one's good too. Okay, so that's our answer here. Moving on to exercise number 3. This is another exercise. This is number 17 from the book, and the instructions cover 17 through 19. It says, use the facts that parallel lines have equal slopes. That one is not going to be relevant to this problem. And that slopes of perpendicular lines have negative reciprocals of one another to solve this problem. So first, let me explain what they mean. Two lines are perpendicular if they meet at a right angle. So these lines are perpendicular because the angle between them is 90 degrees. Negative reciprocal here means to go from the slope of one to the slope of the other, you flip it. So you do, if it's like 5, you go to 1/5. If it's like 2/3, you go to 3/2. So the reciprocal is you flip the fraction. And then you add a negative sign. So if the slope of this line is, let's just make something up. Let's say that it's 7/2. That's 3.5. Then the slope of this, well, you flip the fraction, so 7/2 goes to 2/7, and you add a negative sign, so negative 2/7. Okay, so that's the information that they're giving you, and now let's try to solve the problem. Find an equation for the line through the point 2, 1, which is perpendicular to the line y equals 5x minus 3. Okay, this is another problem where we want to find the equation for a line, and we have some kind of information. In the last one, we had 2 points. Here we have 1 point, and we don't know its slope, but we know the equation for a perpendicular line. Okay, so what we want to find is we want the slope and the y-intercept, just like before. So you kind of have to think, well, what can I glean from the information they've given me? The first thing we'll figure out here is the slope, because we know that our line is perpendicular to this other line. That means if we know the slope of the other line, we can find the slope of our line by taking the negative reciprocal. So what is the slope of y equals 5x minus 3? Let me let you think about that for a minute while I take a sip of coffee. Well, this line it's not exactly in the form of the book. The book writes these as b plus mx, but this is close. You can think about this as mx plus b, where the m here is 5, that's our slope, and the b is negative 3. Now, we don't actually care about the b value for this perpendicular line. We care about the slope. So our line is perpendicular to a line with slope 5. That means the slope of our line is the negative reciprocal of 5. So when you flip 5, it doesn't look like a fraction, but it's really 5 over 1. So when you flip it, you get 1/5, and the reciprocal is negative 1/5. Okay, so now we know the slope. We want to find the y-intercept. And now we find ourselves kind of in the same situation as before, where we want to find the y-intercept of a line. We have the slope, and we have a point. So we can do the exact same trick as before. Our line will look like y equals b, which is the part we're trying to solve for now, plus, I guess it's a minus here because it's a negative, minus 1/5 x. So let's plug in the one point we do know. So this says if I plug in x equals 2, I should get y equals 1. So 1 equals b minus 1/5 times 2. And now we have to solve this equation. So let's, the 1/5 times 2, that's 2/5. And let's add that over to the other side. That tells us that b is 1 plus 2/5. Let's find a common denominator. 1 is 5/5, so that's 5/5 plus 2/5 is 7/5. So we've got our slope, and we've got our y-intercept, and that means we can find the equation for our line. It's y equals b, that's 7/5, plus mx. But our m is negative, so we'll make that minus 1/5 x. And that's our answer. Now again, we can check our answer very easily. So we had two conditions we had to satisfy. We needed to be perpendicular to this line. Well, let's make sure that worked. This had slope 5. Ours has slope negative 1/5, the negative reciprocal. So, okay, check. It also needed to be through the point 2, 1. So let's double check that when I plug in 2, I get 1. So take this right-hand side and plug in x equals 2. That's 7/5 minus 2/5 is 5/5, which is 1, which is what we wanted. Okay, so both of these conditions are satisfied, and that tells us that our answer is correct. Number 4. These are problems 39 through 42 in the book, and we're not going to do all of these. I think I'll do 39 and maybe 41. We'll see how 39 goes. It says, plot graphs based on the following story. As I drove down the highway this morning, at first traffic was fast and uncongested. Then it crept nearly bumper to bumper until we passed an accident, after which flow went back to normal and I exited. So this is giving us a vague story. There's no actual numbers here. And they want us to draw a graph of various different axes. So some variables against other variables. This is a really conceptual question to make sure you understand the idea of independent and dependent variables and how to draw graphs. So these are very important questions to know how to do. So let's look at 39. Driving speed against time on the highway. So let's draw some axes. Now, we know that we're not going to go negative speed or negative time. So let me write a 39 here so it's clear which one I'm doing. So that means I don't need the negative part of my axes. I can just do the positive parts. Now, when it says driving speed against time, what they mean is that time should be your independent variable and speed should be your dependent variable. So let's think about what's happening here now. And by the way, these check marks that you see in some problems, that's just from whatever professor had the book before me. So the check marks don't mean anything. You can ignore those. Driving speed against time. So early on in the drive, traffic was fast and uncongested. So early on in the drive means at some of the beginning parts of time, speed was fast. Now, you might think, okay, well, you're driving, so that means you're like going further, but that's not what we're graphing here. We're not graphing how far you went, we're graphing speed. This would mean, if you had an increase here, this would mean you're accelerating. But it doesn't say anything about accelerating, it just says it was fast. So for some early amount of time, it was fast. And let's make a little mark on our x-axis just for us, for where we move from one part of the story to the other, where it crept bumper to bumper. So let's say crept. And then later we passed an accident. So where it passed. Okay. Now, at some point, it got really slow and went bumper to bumper. Now, because this is a physical problem, a car can't go from really fast to stopped instantly. It has to decrease. So it probably did something like this. And then it crept along for a while until you passed the accident, and then things went back to normal. We're not going to draw the exited part. I guess we can. What does it look like when you exit a highway? Well, you obviously have to slow down. I'm not sure that they intend for us to draw this, but you have to slow down to exit the highway and probably stop at some point before you turn onto the next street. So this is what the graph for number 39 looks like. Now, let's see if we want to do any of these other ones. Distance driven against time on the highway. So that would be time and distance, but let's not do that one. Distance from my exit versus time. Let's do number 41. I think that's going to be interesting. Okay, so let's draw another set of axes here. Oops. Distance versus time. So we have time again on the independent axis and distance from my exit. And let's mark our same events here. So let's say that's where traffic started to creep slowly, and then we passed the accident, and then we exited. Okay, now when are you going to be furthest from your exit? When you start your drive, you're going to be as far from your exit as you ever will be because you're headed towards the exit. So we start some big distance from our exit. As we drive, we're going to get closer and closer. What's going to change here is how fast we get closer. If you're driving 60 miles an hour on the highway, you're approaching your exit very fast. That means your distance is decreasing quickly. If you are driving very slowly, like you're in traffic at 5 miles an hour, you're still approaching your exit, but you're approaching it much slower. And we know that, obviously, when you exit, your distance is 0. So now we have to just figure out what goes on in between here. It should make sense that in between, from here to here, the function is always going to be decreasing. It's always going to go down. It's never going to go up because we're assuming you don't make any U-turns or anything. Initially, you're traveling fast. So you're approaching your exit. The distance is shrinking quickly. But then between when you started being in traffic and ended, you're still getting closer but slower. So it's still a decreasing line, but the slope is shallower. That's the key idea in this one. The slope is shallower. And then now traffic has passed again. And so you rapidly approach your exit. If you were in lots of traffic, it might even look more dramatic where it's something like this. That's up to you depending on how you want to draw it. Okay, so that was 39 and 41. You should definitely try these on your own if you haven't already, and try 40 and 42 on your own as well. One more exercise here. A company rents cars at $40 a day and 15 cents a mile. So you have an initial charge of $40 a day and then an extra 15 cents per mile. And a second company rents them at $50 a day and 10 cents per mile. So a higher initial cost, but then a lower cost per mile. Part A says to give a formula for the cost of renting a car as a function of distance traveled for each company. So let's start there. Let's call them Company A and Company B. And let's say let M be the number of miles driven. Before we write our functions, we have to specify what they all mean. This is really important, otherwise your functions don't have any meaning at all. Let's say A of M is the cost in dollars to drive M miles with Company A. And let's say B of M is the same thing, the cost in dollars to drive M miles with Company B. Okay, now we can write our functions. And these are just going to be nice lines. It starts with A of M. So what is the cost if you drive 0 miles? Well, the problem says that there's an initial cost of $40 a day. And by the way, we're assuming that you're renting the car for a day. So we're not calculating this in terms of like a variable for the number of days you have it. We're assuming you have it for 1 day. So you pay $40 for the day plus 15 cents a mile. Now this is 15 cents, not $15. So that means we need a 0.15 M. Company B has that higher initial charge of $50, but the per mile charge is only 10 cents. So 10 cents is 0.10 M. That's part A. Part B says on the same axes, graph both functions. Now, because these are using both big numbers like 40 and 50 and small numbers like 0.15, we're not going to be able to draw it perfectly. We're just going to try to get a general idea, and then we'll use our little web page here to graph it nicer. Okay, so I didn't really need the negative axes here because we don't expect to have negative days or negative time. Let's just mark 40 and 50. This is definitely not to scale, but we're just trying to get an idea here. Let's use blue for Company A. So Company A is $40 to start with and increases at some slope, which is 0.15. Company B, let's draw in green, it starts at a higher cost, but its slope is shallower. So that means we're guaranteed that at some point it has to cross. Another way we say that is that the two lines intersect. And we know that has to happen because it starts higher, but it's shallower. So it's going to have to cross the line that starts lower and is steeper. So there's our graph, and we'll go into the web graph in just a minute. But let's look at part C. Part C says, how should you decide which company is cheaper? Well, really, I'm not sure if this is the answer they want, but one way to decide is to figure out how many miles you're going to go and plug it into A and B and see which one is less. So plug your mileage into the two functions. And see which is smaller. Now, if this were a pre-calculus question, it would probably say, calculate where the two lines intersect. And I'm not going to waste your time with that. You know how to do that. You set them equal and you solve for m. We'll see that here in this graph. Okay, so this is a blank one because these are the exercises, so we're starting from scratch here. Now, one thing with this graphing calculator, remember this is desmos.com and it's totally free to use. It likes all of the functions to be in terms of x. So even though we had m before, we're going to have x here. So let's call our first function capital A of x equals 40 plus 0.15 x. Okay, so that's one line. Now you might say, well, where's our line? Well, we're only seeing 15 and the line's off the page, so we'll catch up with it in a second. Our second function will make b of x equals 50 plus 0.1 x. Okay, now let's see. Okay, here's our two functions. Company A is in red, company B is in blue. Company B starts out more expensive like we expected. But you can kind of see, especially if I zoom out, that the slope is shallower for company B. So they're going to intersect. And if we scroll over here, we can find the point. It looks like they intersect right here at 200,70. So if you go 200 miles, the cost is the same. If you go less than 200 miles, company A is cheaper. And if you go more than 200 miles, company B is cheaper. That's something that you could have figured out without the graph just by setting them equal and solving for m. Okay, so one starts lower but is steeper, and so they must cross. Okay, so that's all the exercises for 1.1. I want to reiterate here that it's really important that you're practicing these questions on your own. So in addition to the Wiley Plus homework, which is graded, I'm suggesting homework problems for every lecture. We're not going to grade those, but you should think about them in your head as not optional. You should think about them as required, because really there's no way to learn as deeply as you need to with just the Wiley Plus. So you should think about doing the book problems as a required part of the course. It's just a required part that's not graded. And again, the important thing with these exercises in the video is to try them yourself before I do them. And the important thing with the exercises that aren't in the video is to try them once, and you might get stuck. That's an important part of learning. So you try the problem. If you get stuck, then you check your notes, you check the book, you look at the solutions manual, and you see the answer. So you'll look at the answer and you might go, oh, okay, that makes sense. But understanding the answer is very different than being able to reproduce it yourself. So what I really encourage you to do is, if you couldn't solve the problem on your own the first time, make a note of that somewhere. Write down the problem number, and then come back to it the next day, or maybe a couple days later once you've forgotten the answer. Sit down a couple days later, and maybe you can do it yourself from scratch then because you've learned and you've gotten better. Or maybe you have to look at your notes and the solutions again. That's fine. But then write it down again and come back to it a couple days later. If you work out these mathematical muscles enough, you'll eventually be able to do all these problems very quickly and without your notes. So that's my recommendation about the best way to study.